In the Solve It, you maximized your tomato production given some limits or constraints. Linear programming is a method for finding a minimum or maximum value of some quantity given a set of constraints. Constraints. The constraints in a linear programming situation form a system of inequalities, like shown here. The feasible region of that system of inequalities is the graph of the system. It contains all the points that satisfy all of the constraints. An objective function, in this case capital C equals 2x plus y, the quantity you're trying to maximize or minimize is modeled with an objective function. Often this quantity is cost or profit. Graphs of the objective function for various values of c are parallel lines. Lines closer to the origin represent smaller values of c. The graphs of the equations 7 equals 2x plus y and 17 equals 2x plus y intersect the feasible region at the points 2, 3 and 7, 3. These vertices of the feasible region represent the least and greatest values for the objective function. Take note, key concept, the vertex principle of linear programming. If there is a maximum or a minimum value of the linear objective function, it occurs at one or more of the vertices of the feasible region. You can solve a problem using linear programming by testing all of the vertices of the feasible region in the objective function. Problem 1. Testing vertices. This one's multiple choice. What point in the feasible region maximizes p for the objective function p equals 2x plus y? Now take note of our constraints. X plus 2y is less than or equal to 5. X minus y is less than or equal to 2. X is greater than or equal to 0. And y is greater than or equal to 0. Our choices: A, the point 2, 0, B, the origin, C, 3, 1, and D, 0, 2.5. Step 1, graph the inequalities representing the constraints. Step 2, form the feasible region. The intersections of the boundaries are the vertices of the feasible region. Step 3, we'll find the coordinates of each vertex of the feasible region. Those can be labeled as point Q, 0, 0 at the origin, point R, 0, 2.5, point S, 3, 1, and point T, 2, 0. Step 4, having identified the coordinates of each vertex, we'll evaluate P at each vertex. So we'll substitute in the ordered pairs for each of the points representing the vertices of the feasible region, those that we found in step 3. And when we evaluate Q, we find that P equals 0. Evaluating R, P equals 2.5. Evaluating S, P equals 7. And evaluating T, P equals 4. Now of these values, 0, 2.5, 7, and 4, 7 is the maximum value. So S is the ordered pair, 3, 1, that when substituted into our objective function P, yields the maximum value for P. P has a maximum value of 7 when x equals 3 and y equals 1. So the correct choice is C. Your turn, part A. Use the constraints in problem 1 with the objective function P equals x plus 3y. What values of x and y maximize P? And part B, a reasoning item. Can an objective function P equals ax plus by plus c have the same maximum value at all 4 vertex points? Q, R, S, and T. What about at points R and S only? Explain using examples.